Greetings everyone and welcome to the second video lesson for Chapter 6 of the Foundations of Scalable Systems. One of the reasons that websites are so highly responsive is that the internet is littered with web caches. Web caches store a copy of a given resource, for example a web page or an image, for a defined time period. The caches intercept client requests, and if they have a requested resource cached locally, they return the copy rather than forwarding the request to the target service. Hence, many requests can be satisfied without placing a burden on the service. Also, as the caches are physically closer to the clients, the requests will have lower latencies. This slide gives an overview of the web caching architecture. Multiple levels of cache exist, starting with the client's web browser and probably a local organizational-based cache. ISPs will also implement general web proxy caches, and reverse proxy caches can be deployed within the application services execution domain. Web browser caches are also known as private caches for a single user. Organizational and ISP proxy caches are shared caches that can support requests from multiple users. Edge caches are also known as content delivery networks. They live at various strategic geographical locations globally so that they can cache frequently accessed data close to clients. For example, a video streaming provider may configure an edge cache in Sydney, Australia to serve content to Australasian users rather than streaming content across the Pacific Ocean from US-based origin servers. Edge caches are deployed globally by CDN providers. Akamai, the original CDN provider, has over 2,000 locations and delivers up to 30% of internet traffic globally. For media-rich sites with global user bases, edge caches are absolutely essential. Caches store the results of GET requests, and the cache key is the URI of the associated GET. When a client sends a GET request, it may be intercepted by one or more caches along the request path. Any cache with a fresh copy of the requested resource may respond to the request. If no cached content is found, the request is served by the service endpoint, which is also called the origin server in web technology parlance. Services can control which results are cached and for how long they are cached using HTTP caching directives. Services set these directives in various HTTP response headers as shown in this simple example, and in the next few slides we'll delve into exactly how a service can use these directives. The cache control HTTP header can be used by client requests and service responses to specify how the caching should be utilized for the resources of interest. The slide here lists the possible values. No store specifies that a resource from a request should never be cached. This is typically used for sensitive data that needs to be retrieved from the origin server on every request. No cache specifies that the cached resource must be revalidated with an origin server before use. I'll discuss revalidation in a subsequent section in this lesson. Private specifies a resource can be cached only by a user-specific device, such as a web browser, whereas public specifies the resource can be cached by any proxy server. The max age defines the length of time in seconds a cached copy of the resource should be retained. This is essentially the time to live as I described in the previous lesson. After expiration, a cache must refresh the resource by sending the request to the origin server. If max age is not specified in a response, there are two other HTTP headers that can be used to specify how long cached data is retained. These are the expires and last modified headers. Caches have a limited storage capacity and hence must periodically evict items from memory to create space. To influence cache eviction, services can specify how long the resource in the cache should remain fresh. When a request arrives for a fresh resource, the cache serves the locally stored results without contacting the origin server. Once any specified retention period for a cached resource expires, it becomes stale and is a candidate for eviction. Freshness is calculated using the combination of headers. The cache control, max age equals n, is the primary one, and this value specifies the freshness period in seconds. If max age is not specified, the expires header is checked next. If a header exists, then it's used to calculate the freshness period. The expires header specifies an explicit date and time after which the resource should not be considered fresh. As a last resort, the last modified header can be used to calculate resource retention periods. This header is set by the origin server to specify when a resource was last updated and uses the same format as the expires header. A cache server can use last modified to determine the freshness lifetime of a resource based on a heuristic calculation that is supported by web caches. Here we see an example that illustrates how a server can specify how long to keep a resource based on our lift lines example from earlier. When a request is sent for the lift lines for the Blackstone Resort, the response is sent and the cache control setting is set to expire 5 minutes after the date of the response. HTTP provides another directive that can be used to control cache item freshness. This is known as an eTag. An eTag is an opaque value that can be used by a web cache to check if a cached resource is still valid. I'll explain this using an example in the following. Going back to our winter resort example, the resort produces a weather report at 6 AM every day during the winter season. If the weather changes during the day, the resort updates the report. Sometimes this happens 2 or 3 times a day on a stormy day, and sometimes not at all if the weather's stable and sunny. When a request arrives for the weather report, the service responds with a maximum age to define the cache freshness and also an eTag that represents the version of the weather report that was last issued. This is shown on the HTTP example on the slide, which tells a cache to treat the weather report resource as fresh for at least 3,600 seconds or 60 minutes. The eTag value, namely Blackstone Weather 03-2619 version 1, is simply a generated label that the service defines for this particular resource. In this example, the eTag represents the first version of the report for the Blackstone Resort on March 26, 2019. Other common strategies for eTags are to generate the value using a hash algorithm such as MD5. For the next hour, the web cache simply serves this cached weather report to all clients who issue a GET request. This means the origin servers are freed from processing these requests, the outcome that we want with effective caching. After an hour has elapsed, though, the resource becomes stale. Now, when a request arrives for the stale resource, the cache forwards it to the origin server with an if non-match directive as shown on the slide here, along with the eTag to inquire if the resource, in our case the weather report, is still valid. This is known as a revalidation. There are 2 possible responses to this request. If the eTag in the request matches the value associated with the resource in the service, the cached value is still valid. The weather forecast has not changed. The origin server can therefore return a 304 not modified response as shown on the slide. No response body is needed as the cached value is still valid, thus saving bandwidth, and this is especially valuable for large resources. The response may also include a new cache directive to update the freshness of the cached resource. The origin server may also ignore the revalidation request and respond with a 200 OK response code, a response body, and an eTag representing the latest version of the weather report. In the service implementation, a mechanism is needed to support this revalidation. In our weather report example, one strategy is as follows and illustrated here on the slide. To generate a new daily report, the weather report is simply constructed and stored in the database with an eTag as an attribute. When a GET request arrives, the service returns the weather report and the eTag. This will also populate web caches along the network response path. When a conditional GET arrives, the if non-match, the service looks up the eTag value in the database and returns a 304 if the value has not changed. If the stored eTag value has changed, it returns a 200 along with the latest weather report and a new eTag value. If the weather report needs to be updated because the weather has changed, a new version of the weather report is stored in the database and the eTag value is modified to represent this new version of the resource. So in summary, when used effectively, web caching can significantly reduce latencies and save network bandwidth. This is especially true for large items such as images and documents. Further, as web caches handle requests rather than the application services, this reduces the request load on origin servers, creating additional capacity. Proxy servers such as Squid and Varnish are extensively deployed on the internet. Web caching is most effective when used for static data such as images, video, and audio streams, as well as infrequently changing data such as weather reports, as we saw in this example. The powerful facilities provided by HTTP caching in conjunction with proxy and edge caches are therefore invaluable tools for building scalable applications. So there you have it. Don't forget to utilize appropriately application and web caching to scale your systems. In the next lesson, we're going to talk about another essential ingredient of any scalable system, namely asynchronous communications or messaging. Thanks for watching.